All right, so today we are going to continue our discussion about transformations of the quadratic parent function. So in our last lesson, we talked about our shifts. So we had some parabolas that were vertically shifted as well as some that were horizontally shifted. So today, if you look at our learning targets, we're going to graph vertical stretches and shrinks. And we're just going to be able to distinguish among those transformations. So first thing, much like we did in the last lesson, we're going to start out by completing a table, one that is the parent graph, and then one for a transformation, in this case g of x. So like I told you in the last lesson, you kind of have started hopefully to memorize these values. You don't need to show work for the parent function table. Because we should know we're doing -2 squared, which is going to give us 4. Sorry about the handwriting. And then -1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. So smaller table than we had in the last lesson too. So now g of x equals 2 times x squared. According to order of operations, we square the x first and then we multiply by 2. So if you were just making this table, you would probably write out 2 times -2 squared. However, since we already have what x squared is, really we're just multiplying that by 2. So we're taking 2 and multiplying it by 4 in this case. So that's going to give us 8. Down here, the x squared is 1, so we're going to take 2 times 1, which is 2. Then 2 times 0, which is 0. And 2 times 1, which is 2, and 2 times 4 again, which is still 8. So these are our values here. This time in this lesson, they're not making you graph the parent function again every time. They've graphed the parent function for you, and we want to graph g of x on the same coordinate grid. So if we want to add our ordered pair points here, so it looks like we're counting by ones on both axes, so -2 and then all the way up to 8. Then when x is -1, our y value is 2, so -1, 2. Then we've got 0, 0 again, so that's the same down here. And then 1, 2, our symmetric point across, and then 2, 8, which is our point that is across from this one. When you are drawing your parabolas, especially when they get skinny like this, start at the bottom and make sure that it's curvy and not pointy. So try your very, very best to round this bottom. You do not want it to look like, for instance, an absolute value graph like this. Make sure that the bottom is rounded as much as you can. All right, we've got our graph. Now we're going to look at, just like we did in the last lesson, the vertex, domain, range, axis of symmetry for each of these functions. So for the parent function, we already did this in the last lesson, so none of this information has changed. For our parent graph, our vertex is still at 0, 0. Our domain is x between -infinity and infinity. The range, y values for the parent start at 0 and get bigger, so y greater than or equal to 0. And our axis of symmetry is on the y-axis, so x equals 0. If we now go back and look at the values for this transformation, we will notice that its vertex is also at 0, 0. Domain, what is x allowed to be? X is allowed to be any of that. Range, y values, well, since the vertex is in the same place, that means that our range is going to be the same. It also means that our axis of symmetry is going to be the same. So all of these values, even though they are not the same parabola, all of these key features haven't changed for this particular transformation. All right, so now they're giving us a new transformation. So in this case, we had a 2 in front of the x squared. Now in the next one, we have a 1/2. So h of x has a 1/2 in front of our x squared. So again, the parent graph table, we just copy this down because we should know it by heart. by now. And over here on h of x, we're just going to multiply the f of x value by 1/2. So 1/2 times 4. Down here we'll do 1/2 of 1, 1/2 of 0, 1/2 of 1 again, and then 1/2 of 4. So half of 4 is 2, half of 1 is 1/2, half of 0 is 0, and this would be 1/2 again, and this would be 2 again. Just like on number 1, they have graphed the parent function for us here. So we are now just going to plot the points for h of x on the same axis. The reason why we do this where we graph the parent every time is so that you can see the difference. You can see specifically what has happened to the parent graph when we're transforming it. So when x is -2, h of x is 2, so -2, 2 would be right here. -1, 1/2, so that would be here. 0, 0, and then 1, 1/2, and 2, 2. So again, make sure the bottom is rounded. And then draw your parabola. Just like in number 1, now we have our values again. Just copy the same values that we did for the parent. You don't need to go back through and think of it again. We just did this. So vertex 0, 0, domain -∞ to infinity, range starts at 0 and gets bigger, axis of symmetry at x equals 0. If we look at this function, it also has the same vertex, 0, 0. X can be anything again, so domain is going to stay -∞ to infinity. My range, y values start at 0 and get bigger again. And axis of symmetry is the same because the vertex is the same. So notice that these key features had the same values in all 3 graphs, the parent function as well as both of the transformations, g of x and h of x. So number 3 wants us to comment on all of these different features. So it wants us to compare the equations, compare the tables, compare the graphs, and then compare those values. So we can start with the values. We can say that they're all the same. If we look at the graphs, they have those same key features and the same general shape. But what's happened is when I graphed g of x, my first transformation, it's a little bit skinnier than the parent graph parabola is. Still parabola, but a little bit skinnier. And this one is a little bit wider. So when I compare the graphs, I would just say all are parabolas, but g of x is skinnier and h of x is wider than the parent. For the tables, I would say the y values in g of x were greater than the parent. H of x less than the parent. And the equations, we would say g of x and h of x are a constant multiplied by f of x, or the parent. So here it tells us the change in the parent function in item 1 is a vertical stretch by a factor of 2. The change in item 2 is a vertical shrink by a factor of 1/2. So what it wants us to do is it wants us to now say for a is greater than 0, how does the value of g of x equals a to the x change the parent function? So when a is bigger than 0, both of these are bigger than 0. This is a fraction, this is 2, but they're both bigger than 0. So what we would say, item 1, the value was bigger than 1, and that they said was a vertical stretch. So when a is greater than 1, so we already know that this only applies if a is bigger than 0, but if a is bigger than 1, it's a vertical stretch. And we'll say if a is between 0 and 1, again, we can't just say a is less than 1 because we already are assuming that a is bigger than 0. So if a is between 0 and 1, a fraction like the 1/2 here, then that is when we have a vertical shrink. Now, it's important that you understand what it does to the graph. A vertical stretch is going to make the graph skinnier, whereas a vertical shrink is going to make the graph wider. So the way that I like to think about this is think about if you were holding a rubber band. If you take a rubber band and you vertically stretch it, that means the stretch means that you're going to pull, and vertically means you're pulling up and down. If you pull on a rubber band up and down, you're going to make it skinnier. You're going to stretch it. If you were having a vertical shrink, shrink means that you're going to smush it. You're going to press it together. So if you take a rubber band and you push it down, you are making the rubber band flop out wider. So that's what I always think of when I'm trying to remember what a vertical stretch and vertical shrink do, which is, what we've got here in the red. So just make sure that you know what happens to the graph. So you'll have to be able to describe vertical stretch, vertical shrink as the transformation. But because we also have to be able to look at a graph and know its transformation, it's important to be able to recognize that the stretches make it skinnier and the shrinks make it wider. All right, so our next question then, number 5, a change in the position, size, or shape of the parent graph is a transformation. Identify the transformations that have been introduced so far in this activity. So that means not just this lesson, but overall. So in lesson 30-1, we introduced vertical shifts, horizontal shifts, and now we've done vertical stretch and vertical shrink. So now they're showing us that vertical stretching and shrinking also applies to linear functions. And here it gives us the linear parent function f of x equals x that we looked at back, and I think it was unit 3 that we first looked at transformations. So in number 6, it wants us to graph the functions g of x equals 2x and h of x equals 1/2 x on the coordinate grid. So back to reviewing how to graph a line. Remember that we know lots of ways, and you could always make a t-chart just like we have with our parent functions on the quadratic. So t-charts work for any type of graph. So you could use a t-chart, but I'm going to review here how we use slope-intercept form. So g of x equals 2x. If we're looking at it as y equals mx plus b, that would mean that for this function, g of x, m is equal to 2 and b is equal to 0. So if we plot based on that, b equals 0, b is where we start, the y-intercept. M equals 2, a slope of 2 means rise 2, run 1, because it's 2 over 1. So up 2, right 1. Up 2, right 1, up 2, right 1. Also, down 2, left 1, down 2, left 1, down 2, left 1. It's really hard for me to connect these with this pen. There we go. So there is our g of x. If we look at our h of x, if I look at it as y equals mx plus b, h of x in blue, we would have an m value of 1/2 and a b value of 0. So that means that, again, I'm starting at 0, 0. And now my slope is 1/2, so that means up 1, right 2. Up 1, right 2, up 1, right 2, or down 1, left 2, down 1, left 2, down 1, left 2. So now I want to connect those. And we have graphed both of our transformations. All right, so number 6, the question that it asked after we graph it, how do these graphs compare with the parent linear function? So if we look at what's in red, our g of x, where it was a 2, this is a vertical stretch. So for g of x is vertically stretched. Now, we can't say skinnier when it's a line and not a parabola, but what we can say is that it's steeper. So we would say the line is steeper. For h of x, what we have there is a vertical shrink. So it's vertically shrunk. And when we look, again, we can't say it's wider, but we can say that the line is less steep. Oops, can't spell there. Less steep. There we go. All right, hopefully that makes sense. So now what we're going to do is kind of have you try some as far as predicting and understanding what you see in the equation and what you're going to see when you graph it. So if you look at your homework, which starts at 11, these number 12, all of those ones, it asks you to use transformations to graph them. So what you should do is you should write out what the transformation is. So is it a vertical stretch, by a factor of 5? Or is it a vertical shrink by a factor of 1/3? Whatever the case may be, write that out. And then it does ask you to actually graph them. So make sure that you have separate graphs for each one. I don't want these all on the same graph. You should have 4 graphs for number 12. So we're going to kind of practice that. So what we're going to do in 7 and 8 here is the same as what you're going to do in number 12. So predict the change from the graph of the parent. This is the parent. Confirm your predictions by graphing each function on the same coordinate grid as the graph of the parent. So again, make sure that what you do in your homework tonight on number 12 is just like what we're doing on 7 and 8 here. So I'm going to just be quiet for a minute and let you write down what you believe the transformation is going to be, because that's what we're prediction is going to do. So just do number 7 and number 8. Shouldn't take much longer than a minute. So just write down your prediction. It doesn't matter if it's wrong. We'll correct it if it is. But take a minute and just write down your prediction. All right, so now we're going to take a look at what our answer actually looks like. So we're going to do number 7 in red over here. We're going to use the column of my notes to graph these. So we know that our parent function, so x and f of x, if we do -3, -2, 0, oops, I skipped -1. What's wrong with me? There we go. So this we know is 9, 4, 1, 0, 1, 4, 9. And again, I'm just writing that because we should about have that memorized by now. If I make a t-chart now for g of x, which is 3 times the value that's in the parent. So I'm just going to take the value in the parent, which is 9, and multiply it by 3. So I'm going to use these same values here. We may not plot all of them. The 9 times 3 is 27. 4 times 3 gives me 12. 1 times 3 gives me 3. 0 times 3 is still 0. 1 times 3 still 3. 4 times 3 still 12. And 9 times 3 is still 27. So this is my parent on the left. This is my transformation on the right. We're not going to make our graph go all the way up to 27, so we may just do up through -2 on our values here. But I need to draw in some axes. Notice that I don't have any negative y values, so I'm just going to make my coordinate plane the first 2 quadrants. And so here, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Perfect. So 1, 2, 3, 4, 5. This is 5, 6, 7, 8, 9, 10. And I'm actually going to make every other mark useful here so that way we can see it just a little bit better. And I'm not going to plot the -3 values. I'm just going to start with these ones. So on my parent graph, I'm going to leave that in black so we can distinguish it from the transformation. So I've got 0, 0. I've got -1, 1, 1, 1. Then I've got -2, 4, and 2, 4. So my parent graph here looks like this. And then now I'm going to graph my transformation. So I'm going to go back to red. So I've got -2, 12. So -2, 12 would be up here. Then I've got -1, 3. 0, 0 again. 1, 3. And 2, 12. All right, look at us. All done with our graph. Now, we want to see whether your predictions are right. As you can see when we compare the parent to the new graph is skinnier, which means that this had to be a vertical stretch. So, vertical stretch. And then we say how much it's stretched by our A value. So we would say by a factor of 3. All right, so let's check 8 now, see if your prediction was right on that one. So I'm going to use the space over here. I'm going to have to be careful. I'm going to make my tables way down here just because I'm not going to have enough space. So x and f of x. So same as what we had up above. So 9, 4, 1, 0, 1, 4, 9. And then I guess I'll use blue this time for, is it h of x? Yes, x and h of x, which h of x is 1/4 times x squared. So 9 times 1/4 is 9 over 4, which is 2 1/4. 4 times 1/4 is 1. 1 times 1/4 is just 1/4. 0 times 1/4 is 0. And then our values are going to repeat. 1 times 1/4, still 1/4. 4 times 1/4 is 1. 9 times 1/4 is 2 1/4 again. All right, so I should be able to fit all of these values, unlike where they got too big on the last one. So again, I don't have any negative values of y, so that means I should be able to just use the first two quadrants. So I'll do that again here. And, ooh, sorry, that wasn't very straight. So here I'll count by ones just because I don't have quite enough room to make it to 3. So this is 1. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So plotting our parent graph, -3, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. So there's our parent. And now plot h of x. So -3 and then 2 1/4. 1, 2 1/4 would be just barely above it. Then -2, 1, so right here. -1 1/4, so just barely above 0. 0, 0, 1 1/4, 2, 1, and 3, 2 1/4. So if I connect my dots here, there is my graph. We can see by the graph that we have made it wider, which means what has happened here is that that is a vertical shrink. And again, we list how much, so by a factor of 1/4. All right, almost done. Write the equation for each transformation of the graph f of x equals x squared. So vertical stretch by a factor of 5. So that means they're telling you that the a value is 5. So if we want a transformation, we could just make this one g of x equals. The a value has to be 5, so we would just write 5x squared. Vertical shrink, that means it's telling us the h value is going to be between 0 and 1. Factor is 1/5, so we just write 1/5 x squared. Those ones are super simple. All right, so the homework is what you see on the rest of the page here. Again, like I said, you need 4 separate graphs in number 12. One graph, just like we did for 7 and 8, and write out your transformations.